Example 4 says two posts, one 12 foot high and the other 28 feet high, stand 30 feet apart. They are to be stayed by two wires attached at a single stake running from the ground level to the top of each post. So here's going to be the stake. You're going to run a wire to each one of those. It says, where should the stake be placed to use the least amount of wire? So where do you place the stake left and right so that you use the least amount of wire? Again, one of them connecting to a 12-foot pole and one of them connecting to a 28-foot pole. So if we know that they are 30 feet apart, let's call this point, well, if you start at 0 feet, call the first one x feet, then the remainder would be whatever 30 is minus x. So that's how they're getting this x and this 30 minus x over here. So what do we want to do? We want to minimize the length of the wire. So they'll minimize the amount of the wire needed. Well, how much wire is needed? Well, they went ahead and they labeled it in this drawing. Here's y and here's z. So the amount of wire needed would be y plus z. But what I want you to notice is that each one of these makes a perfect right triangle. So this is x, this is 12, and this is y. So if we related this with the Pythagorean theorem being a right triangle, we'd know that x squared plus 12 squared equals y squared. Or what we could say here is that y equals the square root of x squared plus 144. Let's look at the second triangle that we've drawn here. This is a right triangle. This is 30 minus x. Oh, this is going to get nasty. This is a 28, and this is a z. So what's the relationship here? We know that z squared is equal to 30 minus x squared plus 28 squared. So what would z equal? Z would equal the square root of 30 minus x squared. Well, 30 times 30 is 900. So this would be 900 minus 30x minus 30x minus 60x. And then it would be minus x times minus x, so that's plus x squared. And then you have 28 squared, which is 784. So here we'd have z equals the square root of x squared minus 60x. And then you have 900 plus 784, which is 1684. Okay. So, what are we going to do? Well, we can substitute both of those in, y and z, into the original equation. So for the length of the wire that I want to minimize, I would have w equals y, which we said was the square root of x squared plus 144, plus the square root z, which was the square root of x squared minus 60x plus 1684. So because this is what we want to minimize, we need to find the derivative of this. So the derivative of this using the chain rule would be 1/2 times x squared plus 144 to the negative 1/2 times the derivative of the inside. The derivative of x squared plus 144 is 2x. Plus the derivative of the square root of x squared minus 60x plus 1684. Again, using the chain rule, drop the power, would be 1/2 x squared minus 60x plus 1684 times the derivative of the inside, or sorry, to the negative 1/2 power, times the derivative of the inside of that, which would be, 2x minus 60? Okay, simplifying these, the 1/2 and the 2x, the 2's would simplify, so I'd end up with an x over the square root of x squared plus 144. And the next one, the 2's would simplify if you factored out a 2, so that would just be an x minus 30 if we factored out the 2, right? And the 2's would simplify. So I'd have an x minus 30 all over the square root of x squared minus 60x plus 1684. This is my derivative function. So what do I need to do? I need to find the critical values by setting this equal to 0, and where it's undefined, well, where it's undefined is irrelevant because these are both square roots, so the smallest number that it could be is 0. We only care about positives, so what we really care about is when is this thing equal to 0? When is this thing equal to 0? This is going to be messy. This is going to be nasty. There's nothing I can do about it. These are the problems that they chose in the book, and I'm going over the book. So this is x over the square root of x squared plus 144. Sorry, let me go back. 144 is going to be equal to, well, I'm going to distribute the negative. I'm going to subtract it both on both sides. It's going to be negative x plus 30. I'll distribute the negative on top, times the square root of x squared minus 60x plus 1684. Then what I'm going to do is I'm going to cross multiply here. So I'm going to have x times the square root of x squared minus 60x plus 1684. That's going to equal negative x plus 30 times the square root of x squared plus 44. So what am I going to do now? Now I'm going to square both sides. And if I square both sides, you have to square each individual part. So this is going to be x squared times x squared minus 60x plus 1684. On the right, I would have negative x plus 30 quantity squared. Negative x times negative x would be x squared. Then I'd have minus 30x, so that's minus 60x. And then 30 times 30 is plus 900. That's squaring out the x, negative x. Here, let me show you what I did. I squared the entire side, right? And squaring the entire side is negative x plus 30 squared, and then I square the square root. So this would be times x squared plus 144. That's a 144 in there. So what do I need to do? I need to keep on distributing. Let's see what we get. I'm actually going to continue my work up here on the top right. So x squared times x squared would be x to the fourth. X squared times minus 60x would be minus 60x cubed. X squared times 1684 would be plus 1684x squared. On the right-hand side, x squared times x squared would be x to the fourth. X squared times 144 would be plus 144x squared. Negative 60 times x squared would be minus 60x cubed. Negative 60x times 144, let me do that in my calculator real quick. 60 times 144, I'm ending up with 8640, so that's minus 8640, and that would be x. And then I have plus a 900x squared. And then I'd have plus 900 times 144, which I'm getting is a wonderful 129,600. Absolutely ridiculous, but let's figure this out. Okay, so simplifying, I have x to the fourth minus 60x cubed plus 1684x squared. On the right-hand side, I have 1x to the fourth. I had minus 60x cubed. So for the coefficients on x squared, I had 144 plus the 900. 144 plus 900 is 1044x squared plus 1044x squared. And then it looks like I have my minus 8640x. And then my plus 12960. 600. Whew. Set this thing equal to 0. I'm going to subtract x to the fourth from both sides. I'm going to add 60x cubed to both sides. And I'm going to subtract 1684x squared from both sides. And let's see what we get. Actually, a couple of things cancel out. So I have 1044 minus 1684, which is giving me a minus 640x squared. Then I have the minus 8640x, and then the plus 129,600. Okay. What can we do with this? Well, we need to solve this. This is a quadratic equation. Factoring, no thank you. I'm going to use the quadratic formula. So I have x equals negative b, which would be 8640, plus or minus the square root of b squared, so that's negative 8640 quantity squared, minus 4 times a, which is negative 640, times c, which is 129,600. All of that's over 2 times a, which is 2 times negative 640. Again, I'm not messing around. I'm just straight up using my calculator. So I'm going to plug that into my calculator now. So using my calculator, when I put it in with the plus side, I got negative 45 halves. Okay, so that makes no sense for this problem, so I can cross that one out. So I'm going to hit second enter, redo everything that I just did except with the subtraction sign. And when I do it with the subtraction sign, I'm getting a nice number of 9. Holy crud. All that nasty, nasty algebra, all to get x equals 9. You ready for the worst part? How do we prove that this is a minimum? We need to prove that this is a minimum. So what do we do to prove that this is a minimum? Well, to prove that this is a minimum, we need to do the first derivative test or the second derivative test. No way in heck I am finding the second derivative here. So here's what I need to do. 0 is the minimum that I need to consider because that's realistic. 9 is the only critical value I need to consider. So I'm just going to plug in some simple values of 1 and 10. And again, I'm plugging these x values into the derivative function. The derivative function here was x over the square root of x squared plus 144 plus x minus 30 over the square root of x squared minus 60x plus 1684. These look really nasty, but I promise it's not too bad because we know our denominator its square roots must be positives. So let's try plugging in a 1. I would have 1 over the square root of 1 plus 144, 145, okay, and then you do 1 minus 3, so that's a negative value on that second one. That negative value is going to be bigger than the positive value, so that entire interval is going to be negative. I plug in 10, so I'm going to have 10 over something plus 7 over something. That 10 over something is going to be bigger. That ends up being positive. I'm just talking through it. Honestly, put these values into your calculator. So negative over a positive is negative, and a positive over a positive is positive. So I do go from negative to positive, so that's decreasing to increasing. This is a critical value, so I do know that it's a min by the first derivative test. Let's go back and let's look at this problem. It says, where should you put the stake to be placed to use the least amount of wire? The answer would be 9 feet from the 12-foot pole. Not in the middle like you might think. It is 9 feet from the 12-foot pole. We found the derivative, we found the critical value, we proved that it was a minimum by using the first derivative test. Problem was ridiculous. I'm sorry about the algebra, I'm sorry about the numbers. Again, I didn't choose it, these are problems from the book. No, nothing like this would be on the test because that's way too nasty of a function. So let's look at example 5. It says an endpoint maximum. So these are not the typical problems. This is not how it typically happens. Usually your critical values are your maximums or your minimums, but this one is going to have us consider the endpoints as well. So example 5 says 4 feet of wire is to be used to form a square and a circle. How much the wire should be used for the square and how much the wire should be used to enclose the circle for maximize the total area. So what's the idea here? We have 4 feet of wire, so when we add up all the edges of the square in this circumference, that's called the perimeter of the square, by the way, and the circumference of the circle, we have a total of 4 feet to think about. Okay, so let's think about the total area. because that's what we want to maximize, is the total area. Well, the total area would be the area of the square, and the area of the square would be x squared. So here's the area, total area. The area of the square would be x squared plus the area of the circle, and if you remember the formula for the area of the circle, that's pi r squared. Okay, so that's what we want to maximize, is our area, but what we need to do is we need to realize that there are restrictions. Notice that has two different variables in it. It has both x's and r's, so we have to use our restrictions to help us out. And what the restrictions are is the total of the outsides, the perimeter of the square and the circumference of the circle, has to be 4 feet. So let's think about that. To find the wire used, which is 4 feet, we know that we'd have to do the entire square. Well, the outside of the square would be 4 of the x's, so that would be 4x, plus the perimeter of the square, and the perimeter of the square is 2 pi r. So let's solve this equation for r so we can plug it back into that total area equation. So the first thing I see is that I can divide everything by 2 to get numbers a little bit smaller at least. And when I do that, I have 2 equals 2x plus pi r. Okay, so now I want to subtract 2x from both sides. And when I do that, I end up with 2 minus 2x equals pi times r. And then I divide both sides by pi. Well, one thing I notice, it doesn't really matter, but certainly I can factor out a 2 from the left, and I'd have 2 times 1 minus x equals pi r. And then I could divide both sides by pi. And so what I'm left with here is r equals 2 times 1 minus x all over pi. 2 times the quantity, 1 minus x all over pi. So that is what I'm going to substitute into the original equation for the total area. So let's look at this. You'll see why I left it in that form momentarily. So let's rewrite a. So a is going to equal x squared plus pi times, well, r was 2 times 1 minus x all over pi, and then we're squaring that amount, right? So here we have a equals x squared plus pi times, well, let's square each one of those. 2 squared is 4. Then you'd have 1 minus x quantity squared, and that would be all over pi squared, right? But our pi's here can simplify. So what am I left with? I'm left with a equals x squared plus 4 times 1 minus x quantity squared all over pi. So let's get a common denominator, I suppose, because why not? And we would end up with a equals pi x squared plus 4 times 1 minus x quantity squared all over pi. But then what I can do with this is I can distribute out the numerator. So this would be a equals pi x squared plus, well, it would be 1 minus x quantity squared. Foiling that out would be 1 times 1. But then you have the 4, so that would be a 4. Then you'd have a minus x and a minus x, so that's minus 2x, but times 4 would be minus 8x. And then you have a minus x times a minus x, which would be a plus x squared, but then there's the 4, so that's 4x squared. So I just FOILed and distributed all of that, and then all of this is over pi. So what do I look at when I look at that? What I really have here is a equals, well, I can combine the x squareds, so that'd be pi plus 4 times x squared minus 8x plus 4. All of that is over pi. And remember, pi here is just a constant. Okay, I have done absolutely no calculus. The only thing I have done here is some ridiculous algebra to plug in the values for r in terms of x's. So now I need to actually maximize my total area. The way that I do that is I need to find the derivative. Well, the derivative, 1 over pi, is just a constant, so I'll leave that there. The derivative of pi plus 4 times x squared would be 2 times pi plus 4, and then you'd have the x, right? The derivative of negative 8x would just be a minus 8, and then the derivative of 4 is 0. So what I'm ending up with there is 1 over pi times 2 times the quantity pi plus 4 times x, all minus 8. Okay, this is never undefined, but we can set this equal to 0. So let's go ahead and set it equal to 0 and solve this fun equation. So I'm going to multiply both sides by pi. If I multiply both sides by pi, I'd have 2 times pi plus 4 times x minus 8 equals 0. Add 8 to both sides. I'd have 2 times pi plus 4x equals 8. Divide both sides by 2. I'd have pi plus 4 times x equals 4. And so what I end up with is x dividing both sides by pi plus 4. I end up with x equals 4 over pi plus 4. So what is pi plus 4 over pi plus 4? Put that in your calculator, and I'm getting approximately, well, let me do it real quick. 4 divided by pi plus 4. Hit enter, and I'm getting approximately 0.56. Okay, it's not 0.56, but that's approximately what it is. All right, so what's the idea here? Rather than using the first derivative test or the second derivative test, because I don't want to plug any numbers into that first derivative and I don't want to plug any numbers to that second derivative, what I'm actually going to use is the concept of finding absolute extrema on closed intervals. Finding absolute extrema on closed intervals required that we test endpoints and critical values into the original function. Okay, so I'm going to be plugging numbers into the original area function, and I want to think about what are the values that I could have here. Now we got everything in terms of x. So what is the smallest value x could be? Well, we could have no square, in which case x would be 0. What is the largest value x could be? Well, the perimeter is 4x, and that's capped by 4. So that would give me a maximum x of x being 1. So what we need to consider is the interval, the closed interval 0 to 1 for x. That is the closed interval of what we need to consider here. Now to find absolute extrema, the theorem says the absolute extrema must occur. Sorry, let me plug in the x values. You plug in the x values and any critical values into the original function. Again, this is x squared plus pi times, and then it would be 2 times 1 minus x over pi quantity squared. Again, there was a lot that we could have done and plug that in a different place. It doesn't matter which place you plug it into, but that was the idea, is I'm plugging x into there. So what do I need to plug in? I need to plug in 0. I need to plug in that 4 over pi plus 4, because that's the critical value. And I also need to plug in the number 1. So 0 and 1 are my endpoints, the largest and smallest values I need to consider. Let's plug these into the original area function. So if I plug in a equals 0, plug that into your calculator, I'm ending up with a number approximately, I'm just going to estimate it, I'm getting approximately 1.27. If I plug in that 4 over pi plus 4 as the value here, I'm getting approximately 0.56 as my value here. And if I plug in 1, I'm getting a value of 1. And so using the absolute extrema on closed intervals theorem, what I'm deciding is that my maximum is when x equals 0. So the maximum is when x equals 0. And let's reread the question. It says, how much of the wire should be used for the square and how much should be used for the circle to enclose the maximum area? Well, if x equals 0 and we come back and we look, that means I don't want any x's. I don't want any squares. So if I want to maximize the area, all I do is use all of it, use all 4 feet on the circle. So this is an example where the critical value, while it might be a local extrema, a local min or a local max, it is not equivalent to the endpoints here. The endpoint actually provided us with the maximum area. So a very rare case, again, this is absolutely not on the test, but I wanted you guys to see these problems, and these problems progress through the book, and if you read it, it says, you must expect that real-life equations often involve equations that are at least as complicated as these previous 5 examples. So to me, these previous 5 examples have been hell, and what this is saying is real-world problems are at least this difficult. So it says, remember that one of the main goals of this course is to learn to use calculus to analyze equations that initially seem formidable. So it seems like, oh, I can handle this, but what you realize very quickly is you're dealing with nasty numbers. And this is what helps you understand and appreciate the use of technology. Things like Wolfram Alpha that can take a derivative for you and a second derivative for you in a matter of seconds and give you the answer without doing any work. You have to do any work. You can just plug it in. So in the real world, because you're dealing with such nasty functions, such nasty equations, to do optimization problems, they almost certainly are going to be using computer algorithms. Again, though, I need to test that you conceptually know how and why it works and that you can do the algebra behind it. So I'm going to do one of the more simpler problems, something like the box problem that you started off with, where you can do the math by hand yourself and go from there. Okay, so I need to see you do this work. It's not going to be these nasty problems on the test, I promise.